So let's see what we've been up to. So last time we introduced probability distributions, which were a little upgrade to how we model probability. And we also, at the end, had a very nice example of the probabilistic method, which is a fun way to do non-constructive existence proofs by showing that the probability of finding something is greater than 0 and concluding that something like it must exist. Oh, good. All right, so today we are continuing with probability, moving on to a new topic, which is Bayes' theorem. Let me write it properly the first time. Which I'm very excited about because it is absolutely fundamental for working with probability, especially with conditional probability. There are some very nice applications, and some people might say that it even is a nice philosophy for how to think about the world. So I'll say a little bit about that later, but we will start with thinking of it as a nice, simple statement about conditional probability. And then at the end, we will get to another little upgrade for our probability formalism, which is random variables. Let me put that in parentheses. So let's start with Bayes' theorem. And like I said, we're going to build up more and more interpretations of Bayes' theorem, but we're going to start just by pitching it as a simple little equation about conditional probability and give it a quick little proof. So Bayes' theorem says, let E and F be events in some sample space, and let's suppose that they have non-zero probability. This is just a little technical assumption. We haven't seen any examples. We don't normally deal with things whose probability is 0, so this is kind of harmless. Then, so these are basically any two events with this small technical addition, and we have a statement that says the probability of F given E is equal to the probability of E given F times the probability of F divided by the probability of E. So I want to start out by thinking about this just as an equation relating these four probabilities. So let's prove it from that perspective, because the proof is actually fairly simple. So in case you have forgotten, let's recall the definition of conditional probability. So remember, it is supposed to mean intuitively, what is the probability of observing this thing, given that we know this thing has happened? And the way we define it in terms of our probability is that the probability of E given F is equal to the probability of E intersect F divided by the probability of F. And I'll write the similar thing for probability of F given E. That is the probability of E intersect F. You know, this is commutative, so it doesn't matter which order you write it in. But now we're dividing by P of E, because E is the thing that we are given. Right. So now, looking at these definitions, how do we prove this theorem? Well, it essentially comes down to finding probability of E intersect F on both sides and just doing some basic simplifications from there. So rewriting just a bit to separate out this guy from each equation. So here, we essentially just want to multiply both sides by the probability of f. So P of E given f times P of f. This is equal to P of E intersect f. That's just this equation rewritten. And let's do the same thing to this equation, multiplying both sides by the probability of E. Then we get P of E intersect f is equal to probability of f given E times the probability of E. And now we are equating these two sides, the very left and the very right. And if we take that equation and divide by P of E, what we get is, so this cancels out on this side, so we get P of F given E on that side. I guess I'm reversing the order. Equals P of E given F, P of F divided by P of E is what we get on this side. And that, you can see, is exactly what we wanted to prove. So that completes the proof. So really, it follows quite simply from the definition of conditional probability, just with some simple rearrangement. But it turns out to have some quite deep consequences, as we'll see in a moment. But before we move on to that, I want to make one little note. So the way it's written in the book, or an alternative way of writing it in general, is you can write that the probability of f given E is equal to same numerator, but on the denominator, we replace probability of E with probability of E given F times probability of F plus probability of E given F complement probability of F complement. And the reason that we can rewrite it like this, I mean, of course, it's because these things are equal. So let's observe that real fast. So, you know what? No, let's just rewrite it. So E given F times F, E given F complement, F complement. Well, for the same reason that we were observing up here, each of these terms is just, the left one is probability of E intersect F, and the right one is probability of E intersect F complement. And these two things, E intersect F and E intersect F complement, these events are, first of all, disjoint, and second of all, their union is E. So because of that, the probabilities add to the probability of E. So this is just the substitution that we're making to get from this formula to this formula. And the significance is that this formula, or maybe this denominator, is often what you use in practice to compute the probability of E. And so already from this formulation, this one here, we can start to see a little bit of an interpretation coming out of what is Bayes' theorem telling us. So the significance of Bayes' theorem is that F given E and E given F, this thing is not commutative, so these are not the same. And in fact, they often have slightly different flavor. So it's interesting to be able to write one in terms of the other. And what this formula, one way to interpret this formula is saying the probability of F given E, well, that's like if we have observed E, how likely is it that we have F? And this is saying that, so on the bottom, we're saying that if we have observed E, it must be along with F or along with the complement of F, just because one of those things must be true. And we are taking the proportion of those outcomes that came with F, as opposed to the ones that came with the complement of F. Because you can see that this term is exactly the same on the top and the bottom. So we're essentially just taking the, out of all the outcomes that produce E, which is the denominator, how many also produced F, which is this thing. So that is one simple interpretation of Bayes' theorem. But soon we will see some more examples and some more interpretations.